Good morning, everyone. Today I am going to read the chapter Organosulphur Compounds of Organic Chemistry. So, Introduction. Sulfur is placed in the third period of the periodic table just below the oxygen in group 16. During the recent past, a lot of work has been carried out in the area of organosulphur compounds, primarily due to their importance in industry, pharmaceuticals, and metabolic processes. Therefore, in this unit, we shall discuss some important aspects of the chemistry of organosulphur compounds. Structural features. Both oxygen and sulfur alter the chemical nature of carbon atom to which they are attached. But unlike oxygen analogues, in most of sulfur compounds, the reaction occurs by the attack of nucleophile, an electrophile, or even a free radical of the sulfur atom. Another marked difference between oxygen and sulfur compounds is that unlike oxygen, which readily forms double bonds, sulfur is reluctant to form double bonds by pp overlapping. Thus, with the exception of carbon disulfide, thiocarbon compounds are quite unstable and readily undergo addition reactions. In other words, thioaldehydes and most of the thioketones can be generated only as transient intermediates that rapidly undergo dimerization, trimerization, and polymerization to form compounds having only sigma bonds. The instability of the thiocarbonyl compounds is primarily due to the difference in the size of the 2p orbitals of carbon and 3p orbitals of sulfur, which makes 2p-3p overlapping relatively ineffective. In addition to poor 2p-3p overlapping, sulfur is also reluctant to form 3p-3p pi bonds with other sulfur compounds. It is because of the region that elemental sulfur does not exist as diatomic molecule. Instead, it prefers to form only sigma bonds and exist as a nonpolar octaatomic molecule S8 having crown shape as shown in the figure. Further, due to the large size of the sulfur atoms, SS bond is quite low. As a result, the two 3p orbitals one on each S atom cannot come close enough to undergo 3p-3p overlap to a significant extent, and hence the pi bond between 3p-3p orbitals is very weak. It may, however, be noted that unlike thioaldehydes and thioketones, thioamides and thioacids are isolable and hence are relatively stable. This contradicts the generalization that pi bonds involving sulfur atoms are very weak. The actual reason for their stability is the resonance stabilization involving lone pairs of electrons on nitrogen or oxygen atom. Here, the contribution of structure towards resonance hybrid of thioamides and that of the structures toward resonance hybrid of thioacids is significant because both of them have only single bonds between C and S atom. We have discussed above that sulfur has little tendency to form pi bonds through pp overlap. However, many sulfur compounds such as dimethyl sulfoxide, a widely used aprotic solvent, have pi bonds between sulfur and oxygen atoms. As anticipated, this double bond, like any other double bond, consists of the sigma bond and a pi bond. This sigma bond is formed by head-on overlap between an sp3 orbitals of sulfur and one of the half-filled p orbitals of oxygen. The other two sp3 orbitals of S overlap with sp3 orbitals of two alkyl groups to form two additional sigma bonds, while the fourth sp3 orbital contains a lone pair of electrons. Sulfur is now left with a half-filled d orbital, and oxygen is also has a half-filled p orbital. Since dxy lies in the plane of 2py orbital and dzx lies in the plane of 2pz orbital, therefore d pi p pi overlap occurs either between dxy and 2py orbital to form a pi bond. In valence bond terms, this d pi p pi bonding implies that DMSO may be regarded as a resonance hybrid of the following contributing structures. Since DMSO has a high dipole moment, this suggests that the structure makes a significant contribution towards the resonance hybrid, which of course is much greater than that of structure. An important difference between ordinary double bonds with pp overlap and sulfur oxygen double bond with pp overlap is that the groups attached to sulfur do not lie in a plane. This explains why acetone is planar while DMSO is non-polar. Structure of thiols and thioethers. Both in thiols and thioethers, S is sp3 hybridized in the ground state. Such as sp3 hybridized sulfur has two half-filled orbitals which overlap with the sp3 orbital of an alkyl group and a s orbital of the H atom as in thiols, or with sp3 orbitals in two alkyl groups as in thioethers. Each of the remaining two sp3 orbitals contain a pair of electrons. However, due to greater lone pair repulsions than bond pair repulsions, the CSH bond angles decreases from 109 degree to 100 degree in CH3SH. In contrast, in thioethers, due to greater steric hindrance between two alkyl groups than between an alkyl group and a hydrogen atom in thiols, the bond angle in thioethers is larger than in thiols. For example, methyl thioether has a bond angle of 105 degree. Structure of sulfonic acids. In sulfonic acids, S is also sp3 hybridized. Since here we need to form two sulfur oxygen double bonds, therefore both the 3s and 3p electrons are promoted to d orbitals as shown below. The four sp3 orbitals of sulfur form 4 sigma bonds, one with the carbon atom of the alkyl or the aryl group, and the 3 with the oxygen atom. S is now left with two unhybridized d orbitals which overlap with p orbitals of two oxygen atoms to form 2d pi p pi s double bond O bonds. The p orbital of the third oxygen atom overlaps with s orbital of hydrogen to form an OH bond. Thus, sulfonic acids have tetrahedral structures. Nomenclature. For the purpose of nomenclature, sulfur compounds are classified according to the valence state of the sulfur. The compounds containing bivalent sulfur are structurally analogous to the corresponding oxygen. Compounds such as alcohols, carbonyl compounds, carboxylic acids, etc. Therefore, they are often named by adding a prefix thio in the name of the corresponding oxygen analog. For example, thioalcohol, thiophenol, thioethyl ether, thioacetaldehyde. Thiols or thioalcohols, just as alcohols and alkyl derivatives of H2O. In the same way, thioalcohols are alkyl derivatives of H2S. Thus, the general formula of thioalcohols is RSH. In the IUPAC system, thioalcohols are called thiols. They are also called mercaptans, since they react with mercury ions to form insoluble mercury compounds. The functional group of thioalcohols is SH. It is called sulfhydryl thiol or mercapto. A number of sulfur compounds are found in nature. For example, butane thiol is found in skunk, an American animal. Propane thiol occurs in onions. Allyl mercaptan and allyl disulfide occurs in garlic. Nomenclature of thiols. These are named according to the following systems. First, common names. In the common name system, thioalcohols are called mercaptans. The individual name of any thioalcohol is then derived by adding the word mercaptan to the name of the alkyl group. Second, IUPAC system. In the IUPAC system, thioalcohols are called thiols. The individual name of any thioalcohol in then obtained by adding a suffix thiol to the name of the hydrocarbon containing the same number of carbon atoms. In case of isomeric thiols, the position of the SH group is indicated by the lowest possible Arabic numeral. In case of polyfunctional compounds, the thiol is named as the mercapto derivative of the principal functional group. It may be noted that OH group is assigned higher priority both in numbering and naming. Methods of formation. Thioalcohols are generally prepared by the following methods. First, from alkyl halides. When alkyl halides are heated with a large excess of sodium or potassium hydrosulfide, thiols are formed. Second, from sodium alkyl sulfate or p-toluene sulfonic ester. When sodium alkyl sulfate is heated with sodium hydrogen sulfide, thiol is formed. Third, from alcohols. Mercaptans are prepared from alcohols either by treating the phosphorus pentasulfide or by passing a mixture of hydrogen sulfide and alcohol vapors over thoria catalyst at 673 Kelvin. Fourth, from alkenes. Addition of hydrogen sulfide to the carbon-carbon double bond of an alkene in presence of nickel sulfide as a catalyst leads to the formation of thiols. The addition occurs in accordance with Markovnikov's rule. Terminal thiols can, however, be prepared by free radical addition of H2S to an alkene. 5. From thiourea or S-alkyl isothioureonium salts. When alkyl bromides or iodides are treated with thiourea, S-alkyl isothioureonium salts are produced. These, upon alkaline hydrolysis, gives thiols in about 80 to 90% yield. This is the best method for preparing thiols. 6. From Grignard reagent. The reaction of Grignard reagents with sulfur powder gives addition products which upon hydrolysis gives thiols. Physical properties. First, physical state, smell, etc. Methane thiol is a gas while other thiols are colorless volatile liquids with disagreeable smell. The lower members have extremely strong smell while higher members have mild odor. The odor of freshly cut onions is due to the propane 1 thiol and that of the garlic is partly due to the propane 2 in 1 thiol. Small quantities of ethane thiol are added to LPG to warn against leakage of the gas. Second, boiling point. Due to the absence of H bonding in the boiling points of lower thioalcohols have lower than those of the corresponding alcohols. However, thiols have 8 or more carbon atoms have slightly higher boiling points than corresponding alcohols due to stronger van der Waals forces of attraction and weak hydrogen bonds. Third, solubility. Thiols are less soluble in water than the corresponding alcohols. This is due to the reason that thiols cannot form H bonds with water. Fourth, dipole moments. Due to the small electronegativity of S than O, SH bond is less polar than OH bond. As a result, thioalcohols have lower dipole moment than their corresponding alcohols. Chemical reactions. The thiols resembles alcohols in many ways. The main difference in their behavior is towards oxidizing agent. Some important chemical reactions of diols are discussed below. First, acidic nature. Thioalcohols are stronger acids than alcohols. This is because of the two reasons. First, the bond dissociation energy of SH bond is much lower than that of OH bond. As a result, SH bond is cleaved more easily than the OH bond. Second, the anion left after the removal of the proton has a negative charge on S atom, while in case of alcohol, the negative charge is on oxygen atom. Because of the larger size of sulfur, it can accommodate the negative charge more easily than the smaller oxygen atom. Some important reactions of thiols due to their acidic nature are discussed below. First, reaction with alkalis. Due to their stronger acidic nature, they dissolve in NaOH or OH, forming their corresponding salts called mercaptides. The reaction is reversible and the mercaptides are completely hydrolyzed by water in absence of alkali. Second, reaction with mercury oxide. Being acidic, thiols react with mercuric oxide to form mercury mercaptide. Third, action with alkali metals. Alkali metals being strong bases react with mercaptans to form the corresponding mercaptides with evolution of hydrogen gas. Fourth, action of heavy metal salts. When the thiols is treated with the aqueous solution of the salt of a heavy metal, for example lead acetate, a mercaptide is obtained. These heavy metal mercaptides are generally covalent compounds. Second, reaction with carboxylic acids. Thiols react with carboxylic acids, preferably in the presence of an inorganic acid as catalyst to form their corresponding thioesters. The equilibrium lies mainly on the left. However, a good yield of an ester is obtained if acid chloride is used instead of acid. Third, oxidation. Due to the weaker SH bond, thiols can be easily oxidized. The nature of the product, however, depends upon the nature of the oxidizing agent used. With mild oxidizing agents such as the air, H2O2, CuCl2 or sodium hypochlorite, thiols are oxidized to dialkyl sulfides. An alkaline solution of sodium plumbite containing sulfur doctor solution converts thiols into dialkyl disulfides. Dialkyl disulfides can also be prepared by the action of iodine on sodium mercaptides with strong oxidizing agents such as HNO3, periodic acid, etc. Thiols are converted into sulfonic acids. This gives us an important point of difference between thiols and alcohols in their behaviors towards oxidation. Whereas in alcohols, oxidation increases the oxidation state of carbon, while in the case of thiols, the oxidation state of sulfur increases. Fourth, reduction. On treatment with rainy nickel, thiols readily undergo desulfurization to form the corresponding hydrocarbons. 5. Action of aldehydes and ketones. Thiols readily combine with aldehydes and ketones in presence of hydrochloric acid to form mercaptals and mercaptals respectively. For example, acetaldehyde plus ethane thiol gives diethyl methyl mercaptal. When these mercaptals and mercaptols in ethanol are refluxed in the presence of rainy nickel, the thiol group is replaced by hydrogen. Thus, mercaptal or mercaptol formation in acidic medium followed by the desulfurization with rainy nickel gives us an excellent method for conversion of a carbonyl group to methylene group under neutral conditions. This method is however competitive with Clemention's reduction, which is carried out under acidic conditions, and Wolff-Kishner reduction, which is carried out under the basic conditions. Further, these mercaptals and mercaptols on treatment with mercuric chloride in presence of cadmium carbonate regenerate the original aldehyde or ketone. Therefore, like acetals and ketols, mercaptals and mercaptols can also be used for the protection of the aldehydic or ketonic group in the acidic medium. Oxidation of mercaptols. Mercaptols are easily oxidized to sulfanols. For example, oxidation of acetone mercaptols with KMNO3 gives sulfanol. Sulfonal is used as a hypnotic, that is sleep-inducing drug. Homologs of sulfonal, namely trional and tetronal, are even more effective hypnotics. Thioethers. Thioethers may be regarded either as dialkyl derivatives of H2S or alkyl derivatives of thioalcohols. They may also be regarded as derivatives of ethers in which oxygen has been replaced by sulfur. Nomenclature. The common name of thioethers are obtained by adding the word sulfide or thioethers to the names of the alkyl groups arranged in alphabetical order. In the IUPAC system, thioethers are named as alkyl thioalkanes. The sulfur atom is taken with the smaller alkyl group, which forms a part of the alkyl thio group, while the larger alkyl group forms a part of the alkene. The common and IUPAC names of some of the ethers are given below. Methods of formation. First, by heating potassium sulfide with an alkyl halide, potassium alkyl sulfate or potassium tosylate. The yields are generally good to fairly good. Second, by heating an ether with potassium pentasulfide. The yields are often poor. Third, by heating an alkyl halide with sodium mercaptide. This method is similar to Williamson's synthesis and can be used for the synthesis of both symmetrical and unsymmetrical thioethers. Since alkyl sulfide is a better nucleophile than alkoxide ion, the reaction is very rapid and gives excellent yields. Fourth, by addition of a thiol to an alkene in presence of peroxides. 5. By passing a thiol over a mixture of heated alumina and zinc sulfide at 573 Kelvin. Physical properties. First, physical state. Thioethers are colorless, oily liquids having unpleasant smell. Second, solubility. They are insoluble in water but soluble in organic solvents such as alcohols, ethers, etc. Third, boiling points. In general, their boiling points are relatively higher than those of the corresponding ethers. This is due to the stronger van der Waals forces of attraction in thioethers as compared to the ethers, primarily due to the bigger size of sulfur than oxygen atom. Chemical reactions. Although ethers are relatively unreactive, thioethers are quite reactive. Their reactivity is primarily due to the ability of the divalent sulfur atom to get converted into compounds with +4 and +6 oxidation state. The main difference lies in the formation of sulfoxides and sulfones on oxidation and to form sulfonium salts with alkyl halides. Some of the important chemical reactions are described below. First, weak basic character. Due to the presence of the lone pair of electrons on the S atom, thioethers like ethers behave as weak bases. As such, they dissolve in 100% H2SO4 to form sulfonium salts. Second, reaction with alkyl halides. Being sufficiently nucleophilic, thioethers react with alkyl halides by acento mechanism to form trialkyl sulfonium salts. These sulfonium salts are stable at room temperature but decompose on heating to alkyl sulfide alkyl halide. With moist silver oxide, these sulfonium salts form sulfonium hydroxides, which are strong bases. These sulfonium hydroxides decompose on heating to form the original alkyl sulfide and an alkene. This reaction may occur either by E2 or E1 mechanism depending upon the nature of the alkyl groups. If all the groups are 1 degree, the reaction occurs by E2 mechanism. If, however, one of the group is 3 degree, the reaction occurs by E1 mechanism. Third, formation of sulfur ylides and their reactions. The sulfonium salts on treatment with a strong base such as N-butyllithium eliminate an alpha hydrogen to form dialkyl sulfonium methylides, commonly known as sulfur ylides. These sulfur ylides are extremely useful synthetic reagents and have been widely used for the synthesis of epoxides and cyclopropane derivatives by reacting them with a ketone or an activated olefin. Fourth, oxidation. Thioethers on oxidation first gives sulfoxides and then sulfones. First, with mild oxidizing agent. With mild oxidizing agents like HiO4 at 273 Kelvin, oxidation can be stopped at the sulfoxide stage. Second, with moderate and strong oxidizing agents such as H2O2 in glacial acetic acid, diethyl sulfides gives first diethyl sulfoxides and then diethyl sulfones. However, with strong oxidizing agents such as KMnO4, HNO3, etc., sulfones are directly obtained. 5. Reduction. Alkyl sulfides on treatment with Raney nickel readily undergo reduction and desulfurization forming alkanes. 6. Reaction with bromine. Alkyl sulfides form many addition products. For example, addition of bromine gives dialkyl sulfide dibromide. Sulfonic acids. Sulfonic acids are organic compounds having a general formula RSO3H, where R may be any alkyl or aryl group. The aliphatic sulfonic acids are named either by alkyl sulfonic acids or as alkane sulfonic acids, while aromatic sulfonic acids are named only as arene sulfonic acids. Methods of formation. First, aliphatic sulfonic acids. First, oxidation of thiols. Thiols on oxidation with HNO3, KMnO3, NaO, Br, etc. undergo oxidative coupling to form first dialkyl disulfides, which under the conditions of the reaction are further oxidized to the alkyl sulfonic acids via thiosulfonate ester. Second, sulfonation of alkanes. Sulfonation of alkanes with concentrated H2SO4, oleum or chlorosulfonic acids gives alkane sulfonic acids. The sulfonic acid groups generally enter the chain at second carbon atoms, etc. Third, action of sulfuryl chloride on alkanes. The action of sulfuryl chloride or a mixture of Cl2 and SO2 on an alkane in presence of light or peroxide at 313 to 323 Kelvin gives the corresponding alkane sulfonyl chloride in high yields. Here again, the SO2Cl group enters mainly at the second position of the chain through a varying amount of products with the group at the first carbon are also formed. Fourth, Strecker reaction. Sodium salts of sulfonic acids are obtained when an alkyl halide is heated with sodium sulfite. 5. Addition of sodium bisulfite to alkenes. In presence of oxygen or peroxides, anti-Markovnikov's addition of sodium bisulfite to alkenes gives the sodium salt of the corresponding alkane sulfonic acid. Aromatic sulfonic acids. Aromatic sulfonic acids are produced by sulfonation of aromatic hydrocarbons with concentrated H2SO4, fuming sulfuric acid, sulfur trioxide, and 1-protopyridinium sulfonate. The choice of the sulfonating agent and the conditions employed mainly depend upon the type of aromatic compound to be sulfonated. When the aromatic compounds contain an activating group, the sulfonation is usually carried out with the concentrated H2SO4 at relatively low temperatures. In contrast, sulfonation of deactivated aromatic compounds is carried out with fuming H2SO4 at high temperatures. 1-protopyridinium sulfonate is mainly used for the sulfonation of acid-sensitive aromatic compounds such as furan, pyrrole, etc. Physical properties. First, aliphatic sulfonic acids are colorless liquids or low melting solids, while aromatic sulfonic acids are colorless crystalline solids which are highly hygroscopic in nature. Second, the melting points of sulfonic acids are lower than the corresponding carboxylic acid. This is because of the absence of hydrogen bonding in sulfonic acids, as a result of which they exist as discrete molecules, while aliphatic carboxylic acids exist as cyclic dimers due to hydrogen bonding. Chemical reactions. First, acidic nature. Sulfonic acids are completely ionized in aqueous solution. They are as strong as H2SO4. Sulfonate ions is a resonance hybrid of the following three equivalent resonating structures. As a result, negative charge is dispersed all over the three oxygen atoms, and hence sulfonic acids are strong acids. In contrast, the carboxylate ion is stabilized by two equivalent resonating structures. Therefore, carboxylic acids are weaker acids than sulfonic acids. Being acidic, sulfonic acids neutralize alkalis and decompose carbonates and bicarbonates, evolving carbon dioxide gas. Second, formation of acid chloride. When treated with thionyl chloride and phosphorus pentachloride, they form the corresponding sulfonyl chlorides. These sulfonyl chlorides, on treatment with ammonia or alcohol in presence of alkali, form the corresponding sulfonamides and sulfonic esters respectively. Third, formation of anhydrides. On heating with phosphorus pentoxide, sulfonic acids form the corresponding anhydrides. Fourth, replacement reactions of arene sulfonic acids. A number of reagents can bring about the replacement of sulfonic acid groups by other groups. This is because sulfonic acid is an excellent leaving group. This property makes sulfonic acids as valuable reagent in organic synthesis. A few important reactions of this type are discussed below. First, replacement of OH group. When sodium benzene sulfonate is fused with alkali, sodium phenoxide is produced. Second, replacement by NH2 group. When sodium arene sulfonates are fused with sodamide, primary aromatic amines are formed. Third, replacement by CN group. When fused with NaCN, sodium salts of arene sulfonic acid give aryl cyanides. Fourth, replacement by SH group. Sodium arene sulfonates on fusion with sodium hydrosulfide gives thiophenols. Fifth, replacement by H desulfonation. Sulfonation follows the principle of microscopic reversibility. Thus, when arene sulfonic acids are heated with dilute HCl under pressure at 423 to 473 Kelvin, arenes are produced. The mechanism of desulfonation is just reverse of sulfonation as shown below. Sixth, replacement by a halogen atom or a nitro group. When a sulfonic acid group is located at ortho or para position with respect to the OH or the NH2 group, it is knocked off and replaced by the NO2 group or X atom during nitration and halogenation respectively. Sulfonamides. Sulfonamides are derivatives of sulfonic acids in which OH part of the sulfonic acid group has been replaced by NH2 group, or the substituted amino groups such as NHR and NR2 are for example sulfanilamide, N-methyl benzene sulfonamide. Preparation. Sulfonamides are generally prepared by the action of ammonia, primary or secondary amines on the corresponding sulfonyl chlorides. Properties. First, sulfonamides are well-defined crystalline solids and therefore used to characterize sulfonic acids. Second, acidic nature. They are weakly acidic in nature and hence react with strong alkalis to form water-soluble salts. Third, hydrolysis. Sulfonamides with aqueous acid or alkalis undergo hydrolysis to form the corresponding sulfonic acids. Uses. They are used in the manufacture of dyes, antiseptics such as chloramine, tea, and sulfur drugs. Sulfaguanidine synthesis. Acetanilide on chlorosulfonation with excess of chlorosulfonic acid gives para-acetamidobenzene sulfonyl chloride. which upon treatment with guanidine followed by acid hydrolysis gives sulfa guanidine. Guanidine needed for the purpose that is itself prepared by heating cyanamide with ammonium chloride. Uses sulfa-guanidine is an important sulfur drug and it is used for treatment of bacillary dysentery. Since it is only slightly absorbed in the intestinal tract, therefore it is given in relatively large doses. Synthetic detergents. These days, in place of soaps, the substances which are being largely used as cleansing agents are synthetic detergents. As the name suggests, they are obtained from purely synthetic chemicals as compared to the soaps, which are derived from chemicals obtained from natural sources like oils or fats. In fact, synthetic detergents are sodium or potassium salts of long chain alkyl hydrogen sulfates or aryl sulfonic acids. Unlike soaps, synthetic detergents can also be conveniently used even in hard water. This is due to the reason that calcium and magnesium salts of detergent like their sodium or potassium salts are also soluble in water. Hence, synthetic detergents do not form curdy white precipitates with hard water. Further, they can also be used in acidic solutions. However, synthetic detergents have one disadvantage. Unlike soaps, they are not completely biodegradable and hence cause water pollution. The typical synthetic detergents are either alkyl sulfates or alkyl benzene sulfonates. First, sodium alkyl sulfates. They are obtained from the long chain of alcohols by treatment with concentrated H2SO4 followed by neutralization with NaOH. Some important examples of this type of detergents are sodium lauryl sulfate and sodium stearyl sulfate. Sodium lauryl sulfate is also commonly known as sodium dodecyl sulfate SDS. It is mainly used in shampoos and cosmetics. These sodium alkyl sulfates are 100% biodegradable. These are also effective in slightly acidic solutions since they form an alkyl hydrogen sulfates which is a soluble material, whereas soaps react with acidic solutions to form insoluble fatty acids. B. Alkyl benzene sulfonates. The most commonly used domestic detergent these days are linear alkyl benzene sulfonates such as sodium P and dodecyl benzene sulfonate. They are anionic detergents and are obtained by conversion of benzene into long chains of benzene followed by sulfonation and neutralization with NaOH. Another important example of sodium P decyl benzene sulfonate, it is prepared by a Friedel-Crafts alkylation of benzene with a long chain of alkyl halide or an alkene or an alcohol followed by sulfonation and neutralization with NaOH. Alkyl benzene sulfonates in which the phenyl group is either attached to the end of the long alkyl chain or any other secondary position have high biodegradability and hence are called soft detergents, while alkyl benzene sulfonates having branched chains alkyl groups have poor biodegradability and hence are called hard detergents. Cleansing action of soaps and detergents. All the soaps and detergents contain two characteristic groups, that is a water soluble group or an oil soluble. As a result, one end of the molecule concentrates at the surface of the solution or interference. The dirt is generally held to a dirty surface by a thin film or of an oil or grease. When the dirty surface is treated with the soap solution, the non-polar hydrocarbon chain of the soap or detergent dissolves in oil or grease, and the carboxylate group of the soap or the sulfonate group of the synthetic detergent is held by surrounding water. This lowers the surface tension between water and grease. As a result, a stable emulsion of oil in water is formed. When the surface or the cloth is mechanically scrubbed, the loosened dirt particles are absorbed by colloidal soap or detergent particles and ultimately washed away. Thank you.